Welcome back. So, in the last lecture we developed the theory, the quantum field theory using the path integral framework. We developed the Schwinger-Dyson equation for the 5 to the power 4 field. Let us quickly recap where we were last time and then proceed further. And the free field parameters, we have the equation, we have the action functional 1 by 2 mu phi square. The normalization we worked out by doing a Gaussian integration as under root mu upon 2 pi. The probability density function was therefore became under root 2 pi mu upon 2 pi, I am sorry, exponential minus 1 by 2 mu phi square. So, this was for the free field. Then we talked about the interaction represented by phi to the power 4 term in the action. We added this term to the action and we then on the premise that the coupling constant lambda 4 is very small, we expanded this action as a perturbation series in powers of lambda. So, and we found the expressions for the revised normalization, the normalization of the interaction field which is given in the green box, and the expression for the revised generating functional for the Green's functions is given in the red box. The explicit expression for the Green functions, 2 endpoint Green functions is given in terms of the perturbation series as on the slide. And then we obtain the Schwinger-Dyson equation. The general Schwinger-Dyson equation for the generating functional or the path integral as you may call it is given in the first equation on your slide, and for the specific case of the phi 4 field, this equation takes the form of the second equation right at the bottom of your slide. The Schwinger-Dyson equation for the field operator, we found it in two forms. Two expressions are obtained for this Schwinger-Dyson equation for the field operator, number 1 and 2, equations number 1 and 2 given on your slide, and for the field, for the interaction field phi 4, we have this expression which is the bottom equation on your slide. This is the expression for the Schwinger-Dyson equation for the field operator. The Schwinger-Dyson equation for the phi 3 4 field is given in this slide. You see the additional terms involving lambda 3, which is the coupling constant for the phi to the power 3 term to the action, which is included here as an additional term to the original expression for the phi to the power 4 field, which is given in this last equation, bottom equation of this slide. The additional terms comes from this additional term comes from the phi to the power 3 component or the coupling to the free field action. Now, today we start our discussion of the Feynman diagrams. Let us start with a very simple straightforward example. We use the Feynman diagrams for developing or for determining the Green functions, endpoint Green functions of the free field. What we do is we simply take endpoints and connect these endpoints with lines in all possible ways, and we take pairs of points and we connect every possible pair of points, and then we see how we can develop or we can extract the various expressions for the Green functions from this particular diagrammatic representation for the free field. Take endpoints and connect these endpoints in pairs by straight lines in as many possible ways as can be done. For example, for G2 we have only 2 points, because we are talking about G2, we are talking about 2 points, and 2 points can be connected by only one line in only one way. So, we have just the one line being represented here, and we attach a weight because you see, if you look at it, the expression for G2n is given by 2n factorial upon 2 to the power n factorial, and there is an additional expression of 1 upon mu to the power n. To accommodate this additional expression of 1 upon mu to the power n, and there will be n pairs of lines, n lines rather, n pairs of points connected by n lines, and therefore, we attach a weight of 1 upon mu to each line, and that is precisely what is done here. We have got just the one line here, and that one line carries a weight of 1 upon mu. So, we have G 2 is equal to 1 upon mu. Let us look at a more involved case of G 4. Here we have n equal 2n equal to 4, that is n is or we want to determine the 4 point function. So, we talk about 4 points, and these 4 points can be connected with 2 lines. Those 2 lines can be represented in the form 1, 2 or the third one. Please note, the third line is not intersecting, it is moving one, the 2 lines are independent of one another. There is no vertex connect which is the point of intersection of the line 1 and the line 2. They are one is placed independent of the other, but the point is there are 2 lines here, there are 2 lines vertical here, and then we have this cross in this form here, and each of them carries now each line carries a weight of 1 upon mu. So, because we have 2 lines, we have a weight of 1 upon mu square attached to each diagram. Now, because there are 3 possible diagrams, so we have a total weight of 3 upon mu square, which is the value of G 4. Similarly, we can compute G 6 and so on. Let us see the logic behind it. Suppose we need to calculate G 2n, then we take 2n points and connect them in pairs with straight lines in all possible ways. The first point let us say we take any point as the first point, and that first point can be connected to any of the remaining 2n minus 1 points in 2n minus 1 ways. Now, with the first point and being connected to any one particular point out of the 2n minus 1 points, we are now left with 2n minus 2 points. We select the 2n minus 2th point, and the 2n minus 2th point can be connected again to any one of the 2n minus 3 points that are remaining free, that are not connected. So, in other words, we now have 2n minus 1 factorial into 2n minus 1 into 2n minus 3 possible combinations. Similarly, we can continue, and we have a total of the total number of ways in which we can form pairs of we can connect pairs of lines with point connect pairs of points to form lines as 2n minus 1 into 2n minus 3 into 5, 3, 1. First point connected to 2n minus 1 points, then the two of the total 2n points are exhausted. We now have 2n minus 2 points left. We select the 2n minus 2th point, that is connected to any one of the 2n minus 3th point. So, we have 2n minus 3 ways in which that can be done, and then this process continues until we reach the last quantity of last factor of 1, and this factor can be simplified or put in a compact notation as 2n factorial upon 2n 2 to the power n into n factorial. Now, and this is the number of lines. Now, we attach a weight of 1 by mu to each line. So, we have 2n factorial 2 to the power n factorial into 1 upon mu to the power n, and that is precisely what is the value of G 2n as worked out on the basis of the Gaussian distribution. So, this shows the correspondence, at least which is quite simple and which is quite tractable in the free fields case. Now, let us look at the terminology of the Feynman diagram. The Feynman diagrams can consist of the external lines, we have the vertices, we have the internal lines, we have single lines that are ending at a vertex, we have loops, and we have waveforms. The external lines represent incoming and outgoing particles, and they are connected by a vertex. Diagrams are allowed in which one of those lines do not end in a vertex, and they in a sense they simply wander away endlessly. Vertices represent the interaction points. They are intersections of lines. They represent the points of interaction. Internal lines are lines that are connected by vertices at both the ends. So, you have external lines that may be connected to a vertex at one end, and the internal lines are connected to vertices at both the ends. And then you have loops. Loops loops are closed loops are represent internal degrees of freedom. They start and end at the same vertex, and they do not have any bifurcations there. They simply start at one point at a vertex and they terminate at the same vertex. They basically represent internal degrees of freedom that may take infinite values also. We will talk about that. Now, tree diagrams are those Feynman diagrams which do not include any loops. In other words, if we take out from a set of Feynman diagrams, we take out the diagrams that consist of loops or that contain one or more loops, the rest what we get is a tree diagram. Then the source vertex is a vertex at which a single line ends and carries a Feynman rule factor of plus j. This is a source vertex. So, this is some terminology that the viewers need to be accustomed to. Gradually, as we proceed in this course, we shall get more and more conversant with the use of this terminology and the diagrammatics involved with the terminology. So, let us proceed. Time flow can be taken either from left to right or from bottom to up as at the choice of the analyst. Connected diagrams are those diagrams where you can move from one point in the diagram to any other point following the lines of the diagram. And obviously, disconnected diagrams are those diagrams which are not connected. They consist of disjoint pieces that are themselves connected, but they are not totally connected to form one composite piece. In other words, from one point in the diagram, you cannot move to every other point through the lines of the diagram. Now, what are the Feynman rules for the 5-4 theory? For example, as an example, we shall be using the 5-4 theory. To compute, now we talk about the interaction. Recall that in the earlier case, we have just talked about the free field theory. Now, we talked about the interaction theory. We write all Feynman diagrams with p external lines. Suppose we have to compute GP, that is the p point green function. We write all Feynman diagrams with p external lines, excluding vacuum diagrams. What are vacuum diagrams? We will come back to in a minute, but using internal lines and vertices, we write all possible Feynman diagrams with p external lines. The number of external lines must match the order of the green function. For a pth order green function, p point green function, we need to construct Feynman diagrams with p external lines. Every line, as I mentioned, evaluates to 1 upon mu. Every vertex evaluates to minus lambda 4. That is the coupling constant, minus of the negative of the coupling constant, and then there is the issue of a symmetry factor which comes into play. What is the symmetry factor? We shall come back to. In the meantime, if we have a disconnected diagram that evaluates to the product of the values of its pieces. For example, if a disconnected diagram consists of two connected diagrams, then the value of that disconnected diagram is equal to the product of the values of the two connected diagrams. And because of this multiplicative rule, the value of the empty diagram is taken as unity. Now, we come to symmetries, as I mentioned. The Feynman diagrams can be separated into two parts, the inner part and the outer part. The inner part consists of the vertices and internal lines, the outer part consists of the external lines. The inner part is related to the symmetry factor, the outer part is related to what is called the multiplicity. Now, what are the rules for the symmetry factor? These are important. For every set of k lines that may be permuted without changing the diagram, this is important. For every set of k lines which can be permuted without changing the diagram, there will be an added factor of 1 upon k factorial, 1 upon k factorial. For every set of m vertices which can be permuted without changing the diagram, a factor of 1 upon m factorial will be added to the value of the diagram. And for every set of p disjunct connected pieces, that may be interchanged without changing the diagram, you have p disjunct connected pieces and you can interchange them without changing the diagram, then you add a factor of p factorial to the diagram. External lines cannot be permuted without changing the diagram, that is a condition. In this context, the role of multiplicity will come into play. For diagrams without external lines, we have additional possible symmetry, like in the case of loops. The diagrams may be rotated and the diagrams may carry mirror images symmetry, mirror image symmetries. Now, if there is a q-fold rotational symmetry, a factor of 1 upon q comes into play while evaluating the diagram, and if there is a mirror symmetry, a factor of 1 upon 2 comes into play while evaluating the diagram. Now, the symmetry factor cannot be read off, it really depends on the topology of the diagram. So, it cannot be read off from the individual components, the composite set or the composite what should I say, the topology of the diagram, how the various constituents of the diagrams are being connected to form the diagram, have a role to play in determining the symmetry factor of the diagram. Now, a typical Feynman symbols for the 0 dimensional field that we are talking about. A straight line evaluates as 1 upon mu, we have talked about that. A 3 vertex in the context of a phi 3 field evaluates as minus lambda 3, a 4 vertex in the context of a phi 4 field evaluates as minus lambda 4, where lambda 3 and lambda 4 are the coupling constants, and a line with a blob evaluates as plus j. We have already talked about this one. Let us take some examples. These are some illustrations. To explain them, I have separately explained each and every one of them. So, let us take the first one. In the first case, as you can see, there are 5 lines that account for the factor of 1 upon mu to the power 5. 1, 2, 3, 4, 5. There are 5 lines and each line carries a factor of 1 upon mu. So, this evaluates as 1 upon mu to the power 5. In addition, there are 2 3 vertices. Please note the vertices are 3 vertices. This is one 3 vertex and the other is, this one is the other 3 vertex. So, the 2 3 vertices evaluate at lambda 3 squared. Now, the symmetry factor is 1 because there is no internal line which or vertex which can be interchanged. No internal line exists which can be interchanged, no vertex exists which can be interchanged, and therefore, the symmetry factor in this case, in this particular diagram is 1. In fact, in the case of tree diagrams, the symmetry factor is 1 because internal lines and vertices cannot be interchanged. Now, let us look at this diagram. In this diagram again we have 5 lines. So, that accounts for mu to the power 5, 1 upon mu to the power 5. We have 2 vertices as in the previous case. So, we have lambda 3 and both of them are 3 vertices. So, we have lambda 3 square. We have 3 blobs. So, we have j and 3 lines ending with blobs. So, we have j cube, and look the symmetry. If you look at the symmetry, the upper 2 branches, the top 2 branches can be interchanged without disturbing the diagram, and therefore, the symmetry factor is 1 by 2. Here we have a loop with a line. Now, if you look at it carefully, this is a 4 vertex. the point at which the line and the loops are connected is a 4 vertex, where 4 outgoing 4 lines emerge from that vertex, and therefore, it is a lambda 4 vertex. So, we have it evaluates as minus lambda 4. In addition, we have 3 lines, 1, let us call it 1, this is 2 and this is 3. So, we have 1 upon mu to the power cube, and of course, the symmetry represents the symmetry of the flipping of this leaf. So, the symmetry is 1 by 2. You can have the leaf like this, or you can have the leaf like this. So, the symmetry is 1 by 2, symmetry factor is 1 by 2, and the net result is minus 1 by 2 lambda 4 upon mu cubed. Let us look at this diagram here. In this diagram, we have how many vertices? We have one vertex here, which is again a 4 vertex, and we have one vertex here which is also a 4 vertex. So, we have lambda 4 square. How many lines do we have? 1, 2, 3, 4 and 5 lines here. So, we have mu 1 upon mu to the power 5, and clearly these 3 lines can be interchanged without disturbing the diagram. This line 1, 2 and 3 can be interchanged without changing the diagram, and therefore, we have a symmetry factor of 1 upon 3 factorial. Now, in this case, we have two lobes, two connected lobes. We have one vertex, and that vertex is a 4-point vertex. As you can see, there are 4 lines being joined at this point. So, it is a 4 vertex. So, we have 1 lambda 4, the number of lines is 1 and 2. So, we have mu square, 1 line with the first lobe and the 1 line with the second lobe. So, we have mu square, and the diagram has a symmetry factor of 1 upon 2 to the power cube. The flipping of the first leaf, the flipping of the second leaf, and the interchange of the leaves. Now, we come to the concept of vacuum bubbles. I mentioned earlier the concept of vacuum bubbles. The diagrams that contain neither external lines nor source vertices are called vacuum bubbles. Now, the property of this, of course, the empty graph is also a vacuum bubble. The property of these vacuum bubbles is this, that if a particular diagram contributes to a green function, then the diagram together with a vacuum bubble will also contribute to the green function. In other words, if this particular diagram contributes to a green function, then this diagram together with this constituent of the vacuum bubble also contributes to the green function. In terms of interpretation, they really relate to the normalization of the theory. H0, the denominator in the green function, recall the expression for the green function. The expression for the green function was G2n is equal to H2n upon H0, where H0 was related to the normalization. So, H0 is related to these vacuum bubbles. H0 represents the sum of all these vacuum bubbles. So, when we work out the sum of the Feynman diagrams to compute the green function, say G2n, we first of all we include all the possible Feynman diagrams, and then extract away, remove from them all those Feynman diagrams that constitute vacuum bubbles. So, H0 is equal to summation of all vacuum diagrams. All these vacuum diagrams, in other words it amounts to, what I am saying amounts to, that when we work out the green function using the technology of Feynman diagrams, we sum over all Feynman diagrams excluding all vacuum bubbles. Putting it either way, either you sum over all Feynman diagrams and then remove the vacuum bubbles because they represent the normalization, or you sum over all Feynman diagrams excluding the vacuum bubbles. So, hence all that is what I mentioned, every GP will exclude all vacuum diagrams because that vacuum diagrams constitute the normalization, relate to the normalization. This is an example of what the vacuum bubbles would look like for the phi 4 theory, and H 0 is equal to the empty diagram plus the 2 lobes plus the 2 lobes plus 2 lobes and so on. The evaluation of this diagram the empty diagram values at unity. The evaluation of the second diagram we have already discussed, it is minus 1 upon 8 into lambda 4 upon mu square. And the third diagram evaluates to the product of the two diagrams, first and second, plus the additional symmetry due to transposition and so on. Now, so diagrams for G2, for example, G2 will consist of this G2 will consist of the straight line, first the free field propagator of the free field diagram, that is 1 upon mu. Then it will consist of the one vertex or one vertex diagrams, one 4 point vertex, and that is this one. And the second diagram here that evaluates to lambda, lambda being this vertex, and there are 3 lines. So, it evaluates as 1 upon mu to the power 3. The symmetry factor is due to the flipping of the leaf, and similarly the other diagrams can be interpreted. For example, this third diagram has how many lines 1, 2, 3, 4 and 5. So, it evaluates as 1 upon mu to the power 5. There are 2 vertices here. So, lambda square here, and the symmetry factors arise due to the flipping of the leaves 1 upon 2 square, because there are 2 leaves here. So, that is how the evaluation goes. It is worthwhile practicing the evaluation of these diagrams, and one can become proficient through practice. So, for G2 we need to start with diagrams with 2 external legs and excluding all vacuum diagrams. As I mentioned, whenever we work out the green function based on the Feynman diagrams, we need to exclude all vacuum diagrams, and we need to start with those diagrams with the number of external legs equal to the order of the green function. Now, here is a relationship between the moments and the cumulants. Recall that we very frequently migrate between the ordinary green functions and the connected green functions, or the connected diagrams and the ordinary green functions. So, this provides a reference for the migration between the moments and the cumulants. As you can see here, the first cumulant is nothing but the mean, the second cumulant is the variance, the third cumulant is the skewness, and the fourth cumulant is the kurtosis. So, we talked about the symmetry factor, and the symmetry factor basically relates to the internal composition of the diagram, how you can manipulate the diagram, how many ways you can manipulate the diagram without disturbing its original structure in a form, original form in a sense. Multiplicity relates to the external legs of the diagram. It is the number of ways in which the external legs, external lines can be attached in the diagram. So, the symmetry factor relates to the internals of the diagram, multiplicity relates to the externals of the diagram. For example, let us look at the diagram which is shown here. Now, here we have the 1, 2, 3, 4 external legs. Let us enumerate them as A, B, C and D. Now, we can group these 4 legs as A, B, C and D, A, C, B and D, A, D, B and C. So, there are 3 ways in which these legs can be numbered or can be identified without disturbing the structure of the diagram, and therefore, this diagram will carry a multiplicity of 3. So, that is how we need to work out the multiplicity of a diagram, which is also relevant when we compute the value of a Feynman diagram. For example, in this case the multiplicity of this diagram is 3. However, when you attach a source vertex to each of them, the multiplicity becomes 1. Now, we come to a very interesting analysis. We derive the Schwinger-Dyson equation using Feynman diagrams. So, let us start. Let us denote by Cn the number of connected graphs, number of connected diagrams with no source vertices and n external lines, no source vertex, n external lines. A n the set. Now, please note external lines include lines coming into as well as lines going out from the diagram. A n is the set of all connected graphs with one ingoing line and n outgoing lines. Now, we represent this blob by A n, and this obviously it is equal to C n plus 1. We will continue from here. Thank you.